This video will cover section 10.3, the ellipse, or plural ellipses. The objectives will be to write the equation of an ellipse in standard form and graph them. Also to use the properties of ellipses to model and solve some real-life problems, and to find the eccentricities of ellipses, just so you get an idea of what that word means. A circle, a perfect circle, will have an eccentricity of 0 or very close to 0. So if it's the greater it is, the more elongated the ellipse will be, either horizontally or vertically. So before we get to the definition of the ellipse, I want to show you what I mean by vertically or horizontally, and then we will go back to those pages. So I'm trying to find that page. So here we go. So this will be considered a horizontal ellipse, and here we have a vertical ellipse. As you can see here, for a horizontal ellipse, the horizontal axis is the major axis. You could see that here, major axis is horizontal. And for a vertical ellipse, the major axis is the vertical axis. So the way we determine which type we have is by the denominator that will be either with the x square or with the y square. And whatever the biggest denominator is, that will tell you if you have a horizontal or a vertical. So we will do some examples, but just to show you here, we will always use the letter A to denote the biggest or the major axis. And so if the major axis is horizontal, we will have that A square here below the x square. If the major axis is vertical, the a square will be with the y square. And so that is how an ellipse will look with the center at the origin. But of course, not all of those will be center at the origin. So we will be also using H and K, but we will come back to this. So what I want to do is just go over the definition and show you how you can access your ebook again. Because I want to share with you just a few seconds of an animation that is part of your ebook. So let's go to the formal definition. And it says that, by the way, an ellipse is a type of conic. Remember, we discussed that in section 10.2. So if if you have not watched that video, you might want to watch it. So the definition of an ellipse is the set of all points x comma y. So when we say the set of all points, we are thinking about any point that could be placed on the ellipse. Any point. Right here, we're going to use xy as the example. That one. So the points in the plane, and the sum of whose distances from two distant fixed points called foci is constant. So the word foci, or some people call it foci, so will be the plural for focus. As you recall, with the parabola, we only have one focus. With the ellipse, we have two. So we refer to them as foci or foci, or you could Google it. So if we add those two distances, and here we're calling them D1 and D2. So if we add those, D1 plus D2, and let's just say that we get a number, we call it N, just to give it a number. And so that number will remain constant if you were to pick a different point, for example, the one here, and then trace the distance from that point to one of the focus, and then from that same point to the other, like that. And let's call those D3 and let's call this D4. So if we were to add those two, D3 plus D4, we will also get the same distance that we got from the other 2 points. So just to try it one more time, let's select another point. And if we connect that point to the focus, and then to the other focus, and let's call those distances because they're not the same individually, they're only the same when you add them. So let's call them D5, D6. And so if we add D5 plus D6, we will still get the same constant distance, which we are calling here N. So if you have a collection of all those points, then we're talking about several, every single point. And once you put them together, they form that shape, like an oval shape. And we refer to that as an ellipse. Recall from not yesterday, but the previous video that the orbits around the planets, or where the planets orbit around the sun, they are not circles. They're in fact ellipses, and they are not all the same. And that's, some are bigger, but they do have their own specific shapes. So we are actually going to look into that in a minute. So let's go ahead and look at the ebook. So here is your course, and just so you see, you do have an assignment from 10.2. It is due Friday. The assignment for the section 10.3 will be due on Saturday. So again, you go to my ebooks, and we're there. So I'm going to adjust the view. Oh. Okay, so I'm going to select the section 10.3. Okay. And in fact, the there is a very interesting problem that is part of the homework selection about this machine. It's called a lithotripter, and it is actually used to break up kidney stones. And there's an interesting video on YouTube that explains how they work. So I'm going to attach it to Blackboard because you will definitely do this problem. So just so you know how it looks, the problem here. So a lithotripter machine uses an elliptical reflector to break up kidney stones non-surgically. If you ever had one of those, they hurt, and passing them hurts worse. So that is one technique to break them, to make them smaller so that they can just come naturally without surgery. And so they use energy waves at one focus of an ellipse. The reflector directs these waves toward the kidney stone position at the other focus of the ellipse with enough energy to break up the stone. The lengths of the major and minor axis of the ellipse are 280 millimeters. That is 28 centimeters, and 160 millimeters, so that's 16 centimeters respectively. How far is this spark plug from the kidney stone? And so you could see here that there is this spark plug, focus and focus, or I could be wrong about that. And this actually has the answer. So let's see. We have the answer there. So I want to remind you of that some of your questions have the answer, just in case you want to check. And of course, you might get the different numbers, but that's just how college is. So let's go back to this video. I'm just going to play a few seconds of it. And I do like the animation. So there you see it. That's how you could trace one. And that's what we were discussing about the distance from any point. So when you put all those points together, that is what makes the shape. So let's go over some vocabulary. The line through the foci intersects the ellipse at 2 points called the vertices. So vertices is the word, the plural for vertex. So one vertex on the left, one vertex on the right of the center. And remember, the center could be at the origin, but it could also be shifted. So in this case, you could see that the major axis is going to be the vertical axis. And it's right there. Now, the minor axis, it's going to be here. For a circle, both the major and the minor axis happen to be the same, and they actually have a name in common. It's called the diameter. But here we're going to have a minor and a major. So going back to, let me highlight center. So the first line of the slide says that the line through the foci intersects the ellipse at 2 points, and they're called the vertices. So the foci, and they're not really here, but the foci, the 2 points, will always be on the major axis. And I mean, they could be not like midways between the vertex and the center. And so we're going to learn how to find them and where to position them so that we still have the equation of an ellipse, and so that we could actually use that for some problems. There's also a very interesting fact, if I don't make this video too long, which is always um, what I hope, but I end up making them long. But if we have time, I want to share a video about how sound could bounce from, if you were in an elliptical dome or a room, it could bounce off the wall or the dome and then come back to the other point of to the other focus of the ellipse. And there are some interesting stories about Capitol Hill with that fact about being able to listen conversations. So let's hope we have time for that. So right here, we already went over this on the animation. You could trace one yourself. So and you could, decide how wide or how, I don't know, elongated you want it. So I'll leave that slide for you in case you want to try it. You could also just Google a video, and you'll see. So right here, let's get more into the math. And so just like we did with a circle, we have a center, or with the parabola, we call it the vertex. So here we're going to call it center. And that center is going to be denoted by the letters H and K. If the center is at the origin, that means that H is 0 and K is 0. But that will not always be the case. Now, to find the vertices, you will have to, and I just want to clarify that this is a horizontal ellipse. And so for that reason, the number gets added to the x coordinate of the vertex. And so you can see that here of the center, I should say. The x coordinate, that's h. That h is coming from here. And so we're going to add the constant a, and we will see where a is going to come from. So we add the constant a. And then the k, the coordinate of the center will remain the same as the center. To find the foci, we will be adding the constant c also to h, and that is only because we have a horizontal ellipse. If we had a vertical ellipse, we will be adding those constants to k and not to h. So again, h comes from the center, the horizontal coordinate of the center. So let's see where A is located at. So A is going to be the distance from the center to a vertex. And let's draw those here. Remember, the vertex is on the vertices are on the major axis always. So the distance from the center to each of the vertices is considered to be A. So if this is A and this is A, then the distance from one vertex to the other is going to be 2A because it is A plus A, right? So 2A. And there is an equation that we will be using, and that will be a squared is equal to b squared plus c squared. So let's see where that comes from. And before I move on, let's also identify what is b. So not b, I'm sorry, but c. And so c is actually going to be, I'm just going to delete some stuff here. So C, remember that's what we need to find the foci. It's going to be the distance from the center to the focus, to one of them. So the distance from here to here will also be considered C. And you can see that here. That will be the value for C. Sometimes you will be given A, sometimes you will be given B, and you will have to find C. Or you may be given B and C and you have to find A, or you may be given C and A and find B, or I think I already said that, but yes. So you have to be very comfortable with the formula here and also be able to manipulate and know how to solve for the variables. So what I'm trying to say is you might want to write this on your notes. So if you have a squared is equal to b squared plus c squared, and this is only true for the ellipse. Next section is going to be 10.4, which is about the hyperbola, and the equation for that to find b and c is slightly different. So if let's say we want to find b squared, then it will be a squared minus c squared. So you see, this is very different than the Pythagorean theorem. Or if we wanted to find c squared, it will be a squared minus b squared. So you might want to write that down. And then, of course, if the question is find c, then it will be the square root of a squared minus b squared. If the question was find b, it will be the square root of a squared minus c squared. And of course, let's just do this for fun. If we want to find a, then it will be the square root of this part right here, b squared plus c squared. So if we wanted to multiply a by 2, we will also put a 2 right here. So then that will be that 2a is equal to 2 times the square root of b squared minus c squared. And where is that b squared plus c squared coming from? So that, and I'm going to just erase some of the stuff I have here. So as you can see here, we were using the definition of how a point could be, if we take a point and we connect any, and the point could be anywhere on the ellipse. So for example, that point could be here. And if we were to connect the point to one of the foci and then to the other, the distance from those two blue lines added will be the exact same thing as these two lines that I'm highlighting if we add them together. So we proved that on a previous slide. So right now, for convenience, the point has been positioned right above the center. And you could see that is even forming that 90-degree angle. So we could actually say that it is on the minor axis. This is the minor axis and is right above the center. So it's making a 90, if we were to trace a line there, it would make a 90-degree angle with the major axis. Remember, the major axis is the longest one, which in this case is the horizontal. So to calculate the distance from that point to the focus, remember this is the focus, you could see that we have a triangle. And so we already said that the distance from the focus to the center, it's called C. We have it over here as well. And the distance from the center to the point on the minor axis is considered B. So if this is a right triangle with the sides, and we are calling them for convenience, I know that we always call the hypotenuse C, but for this for the purpose of the ellipse, we're going to call one side C and the other side B. So if we were to calculate the hypotenuse for this triangle, it's going to be the square root of c squared plus b squared, and which is what we have here. Now, because we position that point right above the center and is on the minor axis, and we did that for convenience. So then the distance from that point to the other foci is the same. And so it's going to be also b squared plus c squared. So that's how the formula is derived to find the one that we have down here, to find a squared. So using vertex point, if we were to calculate, remember that A is the distance from the center to the vertex, and then C is the distance from the center to the focus, to one of them. So if we were to calculate that and say A plus C or A minus C, and so it will be A minus C, so it will be this little part here. And then if we say A plus C, like we have here, A plus C, so it will be this length plus another piece. This will be A, and then plus another piece. That will be C. And the other one was A minus C, so it will be just like this little part right here that I'm highlighting. So we can add it here. So that length from there to here is actually considered to be two-way. So, or simply the length of the major axis, because remember, if we go from here to here as well, we will have two-way. And so sometimes that could be useful to find the center of the ellipse, because if you know what 2A is, the center will be exactly the midpoint of that length. And so, you know, you'll have to do some subtraction, um, division, or actually adding the coordinates, finding the midpoint, but we will go over those formulas. So right here we have the way that the terms were manipulated by considering those two distances by using distance formula in both cases, and we already know that it is equal to 2A. So I'm not going to go over this because the PowerPoint skips a lot of the steps, and if I do go over them, my video will be so long. So after expanding and reducing the terms and everything, and regrouping, they make the equation look like the one that we have here. And because the distance of b squared, remember how we had this equation first, a square is going to be equal to b squared plus c squared. So if we wanted to solve for b like we did previously, it will be a squared minus c squared. And so that is what we have here. Which implies that the equation of the ellipse is, we substitute, or they substituted, the a squared minus c squared in both cases. They substituted that with b squared, and that's what you can see on the next slide. So the ac minus a squared minus c squared was replaced with the b squared, as you can see there in both places. And then at the end, we divide because we want to have a 1 here. So it makes sense that we divide everything by a square b squared. We do that here as well. And here we can cancel the b squared with the other b squared, a squared with a squared. And so you can see that at the end, we have a squared here. And for the other one, we have b squared. And a squared is very important because that is how you determine which one is the major axis. So in this case, we are talking about the major axis being, wrong color, major axis being the horizontal one. And so that is actually not a square, but that represents A and A. So the length of that axis is equal to 2A. So very important. But on the equation, we're going to use A squared. So if we were to use the same process to derive the formula, we could also arrive to the vertical one. But let's just, I would rather do more examples. So we have here for the introduction slide still, the definition again. Well, it says the standard form of the equation of an ellipse with center at HK and major and minor axes of lengths 2A and 2B. So remember, the major axis will always be, the length of it will be 2A, and the minor will be 2B. So if we have a horizontal ellipse, the A square, because it's the major one, is going to be with the x. And if we have a vertical ellipse, then the a square is going to be with the y. And I say with, but specifically it will be in the denominator. So the foci will also be on the major axis, always. Just like the vertices. And to find that foci, we use this formula. But remember, if you are looking for a square, then you will need c squared plus b squared. And if you are looking for b squared, then you will need a squared minus c squared. So make sure you do have all of these formulas with you. Yes. So if your center is at the origin, then it's like your h is equal to 0 and your k is also equal to 0. So if we were to replace h and k with zeros, then we will get something like what we see here. Just x squared and a y squared by itself if the center was at 0, 0. And this will be a horizontal ellipse because the x squared is below the x squared. And the one here will be a vertical because the a squared is with the y squared. Now, how do we know which one is A and which one is B? Well, always the biggest one is going to be A. So A is always bigger than B. And in the event that A and B were equal, then we wouldn't even be talking about an ellipse. We will be talking about a circle, perhaps. So let's do this again. Major axis is the horizontal axis, so we know that from here, from this vertex to the center, the distance is A, and from that same center to the other vertex, the distance is A, and that's why we call it 2A. That's for the major axis. The minor axis we have is the vertical one, so the distance from here to here is B, and the distance from here to here is also B. And that's why we call that 2B. Now, if we reverse that, then with the vertical ellipse, now the vertical axis is the vertical one. I'm sorry, the major axis is the vertical axis. So this is A, this is A. So we have 2A if we combine the distance from here to here, from one vertex to the other. And for the minor axis, we could see that they have B and B. We add them, so the distance of that is 2B. So we always use A for the major axis. So we're going to work on example 1, and then on this PowerPoint does not have examples 2, 3, or 4. So I'm going to work those out. I got them from the ebook as well, so that we can do more examples. So we have here, find the standard form of the equation of the ellipse having foci 0, 1, and 4, 1. So we do have the solution here, and we do have the drawing, but I just want you to pretend that they're not there. Okay, so we're gonna work them out like if they weren't there. So let's see what we have. We only know those 2 points, and those 2 points are the foci. So we have at 0, 1 and 4, 1. Now, if we were to find the midpoint between those 2 points, and so that's what I'm going to do. I'm going to plot those 2 points. And so we have 0, 1, that would be here, and 4, 1. So 1, 2, 3, 4, and it will be right there. So what I want to do is find the exact midpoint because that midpoint is going to be the center. Now, if you're more of a visual person, you could see that the distance from one of the foci to the other is equal to 4. So it's kind of easy with this one to know that the center is going to be here. And that is going to be at 2, 1. That is the center. So with that, we know that h is 2 and k is equal to 1. So let's see, what else do we know? So at this point, we know the value for C. And because that actually comes from the foci. So C is going to be the distance from the center to the focus or one of the foci. So that's how we know what the value for C is. And that distance happens to be equal to 2. Now, we do know one more thing. It's right here. The major axis of length is, the length is equal to 6. So with that, we know that 2a is equal to 6. So we know that a is equal to 6 divided by 2. So we know that a is equal to 3. So what I know is that the vertex is going to be located 3 units from the center in each direction. Now, since we already have the foci graphed horizontally, that tells me that the major axis is the horizontal axis. You could also tell that the y-coordinate is the same for the foci, so that tells you that what's changing is the horizontal distance between them. So that's another way to determine that is your horizontal, your major axis. So now if I go from the center 3 units to the right, I will be here. This is 5. So I'm going to place my vertex there. And then I'm going to go again from the center, but now to the left, 3 units. 1, 2, 3. And of course, also on the major axis. So that is at -1 right there. And so at this point, we know a lot. We know A and we know C. So it's very easy for us to find, since A is equal to 3 and C is equal to 2, now we just need to find B. And why do we need B? Well, because we need to know the length of the minor axis, but also we need B for the equation. Remember how our goal is to get something that looks like this. X minus h squared. We already determined it's a horizontal ellipse, so the a squared will be here. And then we will need y minus k over b squared. And I forgot to mention this, but we will always have the number 1 as the number after the equal sign. If for an ellipse for an equation that is in standard form, always this will be a 1. So how do we find B? And so I'm going to go back to that formula that we had, and it said that a squared was equal to c squared plus b squared. Also, if we solve for b squared, we will have a squared minus c squared. And that is how we solve for b. So we're going to use this formula here and of course take the square root to actually find b, but you know, b squared will also be used right here to substitute it. So this will be b is going to be the square root of a squared minus c squared. So at this point we know that a is equal to 3 right here. So I'm going to just do the substitution here. So I'm going to put a 3 instead of the a squared. We're going to put 3 squared. And then we know that c is equal to 2. So I'm going to substitute that here. So we're going to have 2 squared. Now please don't subtract the numbers 3 and 2. You have to square them first. Then you will subtract whatever you get out of the squares. So 3 squared is 9 and 2 squared is 4. And the difference between those two is 5. So we're going to get that b is equal to the square root of 5. We leave it as a rational number like that. We prefer to do things like that. But to put it into the equation, we actually need b squared, not b. So once we do that, something will happen. And it will be the square root of 5. But once we square it, it's actually going to cancel the square root and the square. So then we will just use the number 5 for the equation. We will just use the number 5. But the distance is the square root of 5. And the square root of 5 is approximately 2.236. So you can see clearly that it is smaller than 3 because 3 goes with the major axis and b goes with the minor axis. So what it means is that if we were to go 2 units from the center up, 2.236 units up, maybe there, and then 2.36 units below the center. By connecting those 4 points, we can actually trace our own ellipse. And of course, it's not that pretty, but that's why I left the graph here so you can see a pretty one. So again, we have the distance from the focus to the center is equal to 2. That's the value for C. So is here 2, and that's the value for C. And then we had the distance from the center to the vertex was equal to 3, and we found that because we knew the total length was 6. So 2a, that's the total length, is equal to 6. We solved for a, and we found that it was 3. Same goes here. From the center to the vertex is equal to 3. And then we had to find b, and that was right here, b, and that was the square root of 5. So with that, let's go ahead and finish our equation. So for b squared, I substituted that with a 5. Now for a squared, we're going to use 3 and then square it. So 3 squared is equal to 9. And for the x minus h, we do have the values for x and h. And remember, we found them from the midpoint of the foci. So this will be x, here's the h and k. So it will be x minus 2, that comes from here, that's h. And then y minus 1, and because that's the value for k. So here is our answer. That is the answer. The answer, you could also find it here. So yeah, we got it right. Now we're going to move on to example 2. So example 2, this is coming from your textbook. we have to sketch the ellipse, and we have the equation there, and we also need to identify the center and the vertices. So if you recall, I told you that to find the standard equation of the ellipse, and that will allow us to identify the center and the vertices, because for the center, of course, we will need to know H and K. Now for the vertices, it's going to be, and it's actually going to depend if this is going to be a vertical or a horizontal ellipse. So, but one thing I told you is that this number here needs to be equal to a 1. And so the only way we can make it be equal to a 1 is by dividing by 36. So we're going to do that. But if we divide one side by 36, we need to divide the other side by 36 as well. So here what's going to happen is we're going to split the fraction. So we're going to have 4x squared divided by 36, but also y squared divided by 36. And that will equal to 36 over 36. And we did that because we want that to equal to 1. Now for 4 and 36, we're going to simplify it. So both numbers are divisible by 4. So if I divide 4 by 4, I will get a 1. So 1x squared. And 36 divided by 4 is 9. So in reality, I don't need this 1 here. And what I'm going to need here is going to be nothing, because I already have 1y squared. So that's the way I wanted that to look. And as you can see, the center, because we don't have H and K, or we do, but they happen to be zeros. So then the center is going to be at 0, 0. So that's an advantage. Now, a question for you is to identify which one is a square. Is it 9 or is it 36? So a square is always going to be the biggest number. So a square is 36. So if a square is 36, then a is equal to 6. Also, since we have this number here, 9, that is the value of b squared. So b squared is equal to 9. So then b is equal to 3. And so now we actually know a lot, because we know how to find the vertices, and we know that this is going to be an ellipse for which the major axis is the vertical axis. And I'm actually going to draw that again. Okay, so center at the origin at 0, 0. Major axis, vertical axis, and it's actually going to be 6 units up above the center. So it will be right there. And it will also be 6 units below the center. So it's pretty easy to find the coordinates, but in case you don't know, you could also do this. If you want to do it by hand and not like count, they will be, and this is because the center is at 0, 0. So the formula actually says that they are H plus A or H minus A, and comma K. So we're an advantage because both H and K are 0. So for our vertices, we just need A, comma 0 and negative A, comma 0. So in this case, the vertices, as you can see, they are at, So, okay, I did something wrong. I'm gonna correct myself. Sorry about that. It should have been, it's a vertical ellipse. Vertical ellipse, I should probably write it here. Vertical ellipse. So I shouldn't be adding to H. I should be adding to K. I'm so sorry. So this will be H comma K plus A, and then H comma K minus A. And we said because H and K are 0, we're going to have 0 comma 0 minus A, and then 0 comma 0 plus A. So our vertices, you could see they are located at 0 comma negative 6, and the other one is at 0 comma positive 6. There we go. Now we also know the value for B, so we could plot those two other points that will help us connect our points into an ellipse. And those will be, because B is equal to 3, they're going to be 3 units to the right and 3 units to the left of the center. So they will be right there. And of course, we could go ahead and connect the points. I'm trying not to make it too ugly. Okay, and that will be the ellipse. And so we have the center at 0, 0, and we have the vertices at 0, 6 and 0, negative 6. If the question was, what is the major axis? It will be the y-axis in this case, which is, of course, vertical. But also, if they were asking for the equation of the line, that will be the vertical line, x equals 0, as a line, not as a point or as an x value. Now, let's say that the question was identify the foci. So to find that, we will go back to that equation that we had, the one that said a squared is equal to c squared plus b squared. So at this point, we know that a is equal to 6, and we know that b is equal to 9. So I'm going to substitute that. So this will be, let's solve for c squared first. So I'm going to leave c squared on the right side. We have a squared on the left side. I'm going to take the positive b squared across the equal sign, so it will be negative b squared. So now I'm going to substitute a square, so that will be 36, because it's 6 squared, so 36, minus b squared, which is 9, because it's 3 squared, so minus 9. And that will give me c squared. So if I want to find what c is equal to, I'll have to take the square root of those two. So 36 minus 9, and you could already see that it's going to be, what would that be? 27. I was hoping it would be 25, but no. Okay, so right here, the square root of 27. That will be C. Now, the square root of 27, it is approximately 5.19. So you know you're right as long as that value it's below the value that you got for A, which was 6. So it's okay. We could go ahead and graph it. It would just be a little bit past 5. So perhaps there. And then also in the other direction. So there. So the coordinates of the foci, and this is only because the vertex is at 0, 0. they will be 0, comma, if they want the exact answer, I will use the square root of 27, or actually you might have to simplify it. So for 27, we could break that down as the square root of 9 times 3, and that is the same as the square root of 9 times the square root of 3. So the square root of 9 is equal to 3, and the square root of 3, we leave that inside the radical. So instead of writing the square root of 27, my math lab might want you to be a little more specific and actually simplify your answer. So use something like 3 square root of 3. So that will be 0, comma 3 square root of 3 and 0, comma negative 3 square root of 3. Or you could also say 0, comma 5.19, for example, if they were to require an approximate answer and round it to the nearest hundredth, and also 0, comma 2.19. So those are some variations of how you can enter the foci based on what the question is asking you to do. Recall for this question, it was just sketch the ellipse, identify the center and the vertices. So we did that right away. The center was at 0, 0. And we found that by dividing everything by 36. And here was the equation. After that, everything was too simple. So example 3 is a little more complicated, and that is because we have to complete the square. And again, what we're trying to achieve is to get to something that looks like this: ax minus h squared over either a or b square. I don't know which one is going to be the major axis yet, so let's just leave that blank. And then y minus k square equal to 1. So that is our goal for that problem. First, then we will identify center, vertices, and foci. So what we're going to do is take the equation, and we need to have a 1 on the right side. So we are going to rearrange our terms, and we're going to be completing the square, which is not easy. So we're going to write x squared plus 6x. Then we're going to have a plus here, and we're going to leave a space here. Then we're going to continue writing our next term, which will be 4y squared minus 8y. And then we want to move the 9, this 9, to the right side. So since it's adding on the left, on the right it will be subtracting. So it will look like that. Okay, now I'm going to complete the square with the x terms. However, I can't do that with my y terms yet because the coefficient of the y square is a 4. So the only thing I can do is actually factor out a 4. But let's do that in the next step. So first, let's see if you guys remember how we complete the square. So it's x squared plus 6x. And we're going to take half of 6, half of the coefficient here, which is 3. And we're going to square it. And it's positive 3. Now on the right side, first we need to factor out a 4. Or divide these two terms by 4. So if I do that, I will get y squared minus 2y. Now here, I can leave that little space that I need And I'm actually going to need more space here. And we're going to take, we're going to take half. In this case, we're taking half of -2. So that will be -1. And then we're going to square it. Just like that. Then on this side, we still have this -9. But we're still going to either add or subtract some numbers. But let's just leave those blank right now. And they're actually going to come from here and here. But I want to simplify them first. So instead of having 3 squared, let's just call it 9. And then we're going to have plus 4 y squared minus 2y. And if we square one square, we're going to get +1 because it's -1 times -1, that's +1. Okay, so now on our right side of the equation, we already know that we have a -9, but now we need to add, or in fact, we're going to subtract, or let's use it this way. So we're going to have, since we added 9 here, it's a +9, then we have to subtract it on the other side. And I'm sorry, I'm wrong. If it was on the same side, we will subtract it. But we're just going to do it to both sides. So this will also be a +9. That way we keep things balanced. We add 9 on the left of the equal sign, but we also add 9 on the right side of the equal sign. Then we're going to add the same number that we added here. And this is the tricky part. We're not only going to add a 1, we're going to add a 4 times 1, because remember we factor that 4 out, so it still has something to do there. So that will be 4 times 1 is 4. So remember, we do that to keep the equation balanced, so it's still true for both. Okay, so now we're gonna, the purpose of completing the square is so that we can factor in this way into a binomial. So this will be x, and we actually use this number, +3. For the other one, we factor it, and it will be, actually, I'm forgetting about the 4. And then we factor y. And in this case, we're going to use a -1, because that was the half of this number, -1 and square. Now, what do we have on the right side? We have 9 minus 9, or -9 plus 9 is 0. Plus 4 is going to equal to 4. So we're almost there. Now, remember how we need to have a 1 here by itself. So we're going to divide everything by 4. So if I do that, I'm going to have the following. X plus 3 inside parentheses square divided by 4. And then here for this 4 and this 4, they cancel. But remember, they don't disappear. They equal to 1. So this is going to be y minus 1 squared over 1. And then on the right side, pretty clear that 4 over 4 is 1. So now we do have our equation. And remember, the biggest number is a squared, always. So we know from here that a... okay, I apologize for that. Okay, so like I was saying, the biggest number here is clearly to be 4, so that is actually a square, 4. And the other number here, this one, is going to be, because it's smaller, that's considered to be b squared. So from there, we're going to find that a is equal to the square root of 4, which is 2. And then b is gonna be equal to the square root of 1, which is 1. So from there, we already know a lot. So I'm gonna make more space here. And from right here, we're gonna find c. So c squared is equal to a squared minus b squared, or c is equal to the square root of a squared minus b squared. So c is going to equal to the square root of 2 squared minus 1 squared. So that tells me that c is equal to the square root of 4 minus 1. So c is going to be equal to the square root of 3. Why do we need to know that? And actually, let's get the approximation for c. 1.73. And so you see, as long as you get a small number smaller than a, then you know you're okay. So why do we need to know the value for c? Well, because with that, we will find the coordinates of the foci. So first, where is my equation? Okay, so it is here. So remember too that we also need to find the center. So for the center, we will be using the values for h and k. And those are going to be in the equation. However, we're going to have to use the opposite of what we see here. So we see a plus 3, our center is going to be a negative 3 for the x coordinate. That is because the formula comes with a minus already embedded into it. So you have a double negative, and that's what causes the equation to look like it's a positive 3. Now for the k value, we see a negative 1 here. So then we take the opposite. We call this counterintuitive. So it will be positive 1. And that will be the center. Negative 3, 1. So for the foci, well, also it's important to identify what type of ellipse we have. And since you see the biggest denominator being with x, we could say that we're going to have a horizontal. So this is very important to find, horizontal ellipse. And if we want to graph it, I'm kind of out of room. So if we want to graph it, it will be the center at negative 3, 1. So 1, 2, 3, and then positive 1. So it will be here. And maybe I'll make this a little bit bigger. So I plotted the center at negative 3, 1. We know it's a horizontal ellipse. So then the foci is going to be this many units, 1.73 units, to the right and to the left of that center. So it will be the formula for it, because it's a horizontal parabola. Ellipse. It's going to be h plus c, comma k, and the other one will be h minus c, comma k. So the foci, the coordinates for it, they will be at negative 3 plus, I can use the square root of 3 as well, comma, the value for k, it was in the center, is a 1. Or the other one will be negative 3 minus the square root of 3, comma, 1. And of course, if they want the exact answer, you just leave it like that. But if they want an approximation, then you will do that. So those are the coordinates to approximate the foci. So yeah, there will be like, I don't know, there and there, somewhere there. And then finally, to find the vertices, since A is equal to 2, the formula for that, let's just make sure we have this here. So the formula for the vertices, because again, we're talking about a horizontal ellipse, they will be at h plus a, comma, k, and the other one will be at h minus a, comma, k. So the vertices will be at, well, I'll write it on the side. So there will be -3. The value for a was 2, so it's going to be -3 plus 2, comma 1. That's the value of k. And the other one is going to be -3 minus 2, comma 1. So then the two vertices will be -3 plus 2 is -1, so -1, comma 1. And the other one will be at -5, comma 1. So of course we could graph those. So we had like 4 is here, maybe 5 is here, and the other one was at, what is it, -1. Okay, so we're talking about points that are perhaps, I'm going to zoom in a little bit so you can see better. So that will be one of those vertices. And then the other one will be like right here. Of course, my graph is not perfect. And because the value of B was, I believe it was, I'm not sure. It was a 1. Okay, so that will be easy. I can just go 1 unit up here from the center and 1 unit down to right here. And then we connect our points. And there we have our ellipse. So major axis, minor axis, vertex, vertex, plural vertices, focus, focus, plural foci. And some people call it foci. I really don't know who's right. So we're going to get back to the slides, and I know I have another problem here. I don't want to do the whole graphing process. However, I just want to do the completing the square one more time, because I know people tend to struggle with that. So we have the equation here in general form. We want to turn it into standard form. So we're going to group the 4x squared with the -8x. Then we're going to take the y square, group it with the 4y, and then we're going to move that -8 to the right side of the equal sign, so that will be +8. Then here I need to factor out a 4, so 4 times x squared minus 8x divided by 4 is 2x. I need to do that so that I can actually complete the square. Then I'm going to have y squared plus 4y. I don't need to factor anything there because the coefficient of y squared is a 1 already. And then parentheses, and then we have here our number 8. And I'm actually going to make some room here. So we're going to have that, and then remember we're going to have to add some stuff as well. The stuff that we're going to put inside these boxes. Okay, so what goes in that box? Well, we're going to take half of -2, which is -1, and square it. And then we're going to take half of 4, which is +4, which is 2, and then we're going to square it. Okay, so the same numbers that we're adding or there, we're going to add them to the other side because we want to keep our equation balanced. Keep in mind that once I square the -1, it's going to turn positive. So we have 4 times x squared minus 2x plus 1. and then plus y squared plus 4y plus 4, because that's 2 squared. So here we're going to have 8 plus, and in fact, oh, big mistake. We're not really adding that. We're adding 4 times 1. So we're adding 4 times that 1. So in reality, we're adding 4. And here we're adding another 4 because that is what 2 squared is. So instead of just adding 1, for that one is 4. Okay, so now we're going to factor this. So it will be x minus 1 squared. For the other one, we're going to have y plus 2 squared. And on the right side of the equal sign, we're going to have 4 plus 4 is 8 plus 8, 16. So now here, you know, on the right side of the equation, we want to have a 1. So we're going to divide everything by 16. And that way, we will have a 1 here. Here we can leave the y plus 2 squared and the 16 like that. And then here we have a 4 and a 16. Both numbers are divisible by 4. 4 divided by 4 is a 1. And 16 divided by 4 is a 4. So we're going to have 1 times x minus 1 squared over 4. So now in this case, you could see that we're going to have a vertical ellipse. Why? Because the denominator of the y square is bigger. So that's how we know it's vertical. So that tells me that a squared is 16. So therefore, a is a 4. And we know that b squared is coming from here. So it's a 4. So therefore, b is equal to 2. Now for the center, it's very easy. You have to use your counterintuitiveness. So if you see a negative 1 here, you put a 1 here. And if you see a positive 2 here, you put a negative 2 here. That is the center. And you have your values for A and B. So it's pretty easy to find C. And I'll write the formula here. C squared is equal to A squared minus B squared. So I'm going to leave it there. But just to point out that when you do, let's just finish it. We're almost there. So C is going to be equal to the square root of A squared, which is 4, minus B squared. I'm sorry, 4 squared minus B squared, so 2 squared. So this is equal to the square root of 16 minus 4. So C is going to be equal to the square root of 12. Which if we simplify it, it should be the square root of 4 times 3. So if we take the square root of 4, it's a 2. We take it out of the radical, and then we put the square root of 3 right there, like that. So in this case, for the vertices, because it is a vertical ellipse, we will not do anything to h, but we will be making the changes to k just because it's vertical. So it will be k plus minus, remember, one of each. That will be the value for a. And for the foci, it's going to be h plus minus, no, not 2h. Remember, we're doing a vertical ellipse. So k plus minus c. And that is how you will find your 2 points. So as I mentioned before, the planets have elliptical shapes as their orbits. Also, satellites, they orbit in an elliptical way as well. So the next example, which they're calling 4, but I'm going to call it 5 because we already did 4. So this one, it talks about that. And it's an application involving an elliptical orbit. So the moon travels about Earth in an elliptical orbit with Earth at one focus as shown below in this figure. The major axis, the major and minor axis of the orbit have lengths of 768,800 kilometers, and that would be for the major axis because it's bigger. That's how we know. So that is this one. And if you see this elliptical shape, this ellipse, it's almost a circle, almost. But because the lengths of the major and minor axes are not equal, it's not a circle. So here's the minor axis. Okay, and we have respectively. So find the greatest apogee and least perigee distances from Earth's center to the moon's center. And you could see those two words, the greatest, it's going to be here. And then the least perigee is going to be here. So we're talking about the distance from here to here, from here to here, and then from here to here. And for some reason, is the Earth, remember this is the orbit of the moon, and this is actually very interesting. Our planet Earth is not at the center of that orbit. So the moon rotates almost in a circular way, but it's an ellipse. However, the Earth is not the center. And that's why you can see that one of them is longer. The distance from here to here is longer. That's the greatest distance. And it does have a name, the apogee. So most of the solution is already here. I didn't delete the solution. So we could see how based on the numbers that we have, the length of the major axis, remember, that was given to us. So that is considered to be 2a, right there. That came from here. And so to solve for a, of course, we just have to divide by 2 on both sides. So if we divide by 2, we get a is equal to this number. Now for b, we have the length of the minor axis, so that's here, and that will be equal to 2b. So to solve for b, of course, we divide that number by 2 and we get this number. So now to find c, remember we have that formula that says that c squared is a squared minus b squared. And so if we take the square root, that's how we find c. So that's how c was found right here. And it happens to be that big number. So from there, we know that the greatest distance between the center of Earth and the center of the moon is going to be a plus c. And we happen to know both numbers. A is here, c is here. So if we add those two numbers, we will get 405,508 kilometers. So that is I believe that is the apogee. Yes, the biggest one. And then for the least, we calculate a minus c. And so we do know what is A, we know what is C, and that gives us this number, and that will be the, let me get the name again, perigee. So I mean, if you take astronomy, you will find this pretty useful, I imagine. Okay, one last term, eccentricity. So one of the reasons it was difficult for early astronomers to detect that the orbits of the planets were ellipses is that the foci of the planetary orbits are relative close to their centers. As you could see with some of our graphs, you know, we had the ellipse and then the vertex here and then the centers here, and perhaps the, well, for this one it was a bad example. The foci will be something there. But if we had an ellipse that was more like the orbit of the moon, the the foci is actually very close to the center of that orbit, because it's closer to a circle. So in fact, when the eccentricity is close to zero, then it will look more and more like a circle. So to define the eccentricity, we get the ratio of C over A. And that is the formula that you will be using. So the eccentricity is a value that goes from 0 to 1, meaning that, for example, if you had, let's see, C, uh, if C and A were equal, it will be a 1, but it cannot equal 1 because you don't see the equal part here for the inequality, so it's just less than 1. And it cannot, if, okay, this might sound a little weird, but if A and C were equal, yeah, I'm not sure. Maybe it will be a line. But if A and if the eccentricity was close to 0, the closer it gets to 0, the more circular it gets. So I'm imagining, yeah, that the closer it gets to 1, it will start looking like a line, like either horizontal or vertical, but I could be wrong. Anyways, so it's very simple to find it. Just divide C over A. You already know how to find A. You already know how to find C. And you know how to find B, depending on what you have. So based on that, you could answer some questions. And right here we have, just so you get an idea of the orbits, we have the eccentricities for the planets. And the orbit of the moon has a very small eccentricity. As you recall, it almost looks like a circle because the major and minor axes are very close in length. And then the other ones, as you could see here, for example, the biggest would be Mercury. So that tells me that it's a more, perhaps a more elliptical, more elongated orbit, more than, let's see, perhaps, what's a good example? Maybe Mars is more like that. And then if you look at the one for Venus, it's even smaller than the one for the moon. So I imagine that one is more of circular shape. So that is the end of the video, finally.